As we're coming to the end of this series on how to quickly and efficiently find the zeros for most polynomials, hopefully our approach is becoming clear. The basic idea is that we're going to take a given polynomial and we're going to graph it using our graphing calculator or some other graphing utility. And that allows us to quickly ferret out any real roots that the polynomial may have, including information about the multiplicity of those roots. Then we can cut to the chase using some synthetic division or long division as needed and break the polynomial down to the extent that it's possible. If you have a blend of real and complex roots, you're probably going to end up using some kind of quadratic formula or factoring pattern in order to resolve the complex roots. And so this, when you're practiced, permits you to, within a few minutes, very quickly and efficiently break down a polynomial into factored form. Let's take a look at our next example here. You can see that we have a 4th degree polynomial, and the instructions are the same as the prior installment. We're being asked to break this down into factored form. So I've taken the liberty of keying it into the graphing calculator just to save a little bit of time. If you want to test yourself here, you could pause the video, key it in for yourself, see how you do. Let's switch to the calculator. There's the polynomial right there, 4th degree, so we know that we're looking for up to 4 roots, depending on the multiplicities. And I think a good starting place here would be to graph this just using a standard zoom. So I'll zoom 6 it. Now you can see the window settings, hash marks on the x-axis are 1 unit apart, likewise on the y. So I can just read that. It looks like I have a root at -1 and I have another one at 3. Let's verify that. Definitely a root at -1. Definitely a root at 3. And they both appear to have odd multiplicity. So let's go back to the iPad here and see what we can do. So I'll start with the root, and let's just say here what we found via calculator. I'll just start with the root of -1. When you're doing synthetic division on a root as opposed to a factor, you just drop the value of the root into the divisor box. You don't have to change the sign, right? So the coefficients would be as follows. It's 1, -2, -2, -2, and -3. And let's see what we get here. -1 times 1 is -1. -2 plus -1 is -3. -1 times -3 would be +3. -2 plus 3 is 1. -1 times 1 is -1. -2 and -1 is -3. -1 times -3 is +3, and as expected, we get a 0 for our remainder. There really is no sense in reporting out at this time. It really doesn't give us anything. We're just trying to break this down as efficiently as possible, and so it makes the most sense to just go right into the next round of synthetic division with the root at 3. Bring down the 1. 3 times 1 is 3. -3 and 3 goes away. 3 times 0 is 0. 1 and 0 is 1. 3 times 1 is 3. And then -3 and 3 go away. And so if you build your answer right to left, that's x to the 0, x to the first, and x squared. And so at this point it's clear from just a few seconds of quick synthetic division that our polynomial is as follows. We're going to have x plus 1. That's from the root at -1. We're going to have x minus 3. That's from the root at 3. And then we're going to have x squared plus 1. And as mentioned, x squared plus 1 can be factored using difference of squares. So your final answer here would be p of x is, and by the way, that's difference of squares over the complex numbers, not over the real numbers. But anyway, here's what you have. You have x plus 1. You have x minus 3. And you have x plus I and x minus I. And that was very straightforward and easy. Now, had I obtained something here at this step which was not resolvable using a pattern like difference of squares, I would use the quadratic formula. Let's see what we have next here. And by the way, before I forget, sort of at the risk of belaboring the obvious here, I usually like to list, just for clarity, what I've found, because their primary interest is the roots and the multiplicities typically. So if you're making such a list for this example here, here's what we found. So we had a root at -1 and it had a multiplicity of 1. We found another root at 3 and it had a multiplicity of 1. And then we had roots at plus or minus I, or if you prefer, you could say 0 plus or minus I if you want to be real wooden about it. And those are 1 each. Never hurts to be clear about things, right? So a couple more examples in this vein, and obviously we're trying to move to more challenging problems as we go, and so that's why these were chosen, let's put it that way. Now this one right here that you can see on the screen is a really nice problem, and so if you watch these other recordings and you're thinking, wow, I got this down, I would say, well, have a go at this one, because this one is really good. So you can pause the recording and see how far you get. Let me show you what I've got. Now you can see this is a 5th degree polynomial, and I've taken the liberty of keying it into the calculator just to save a little bit of time. Let's have a look at the graph. Looks correct. X to the 5th plus x cubed plus 8x squared plus 8. Okay. I'm going to just zoom 6 it. And there's the graph. So it's interesting. I have a root at -2, it would appear. Let's verify that. For sure. And it has odd multiplicity. So we're expecting a total of 5 roots, but we don't know, whether it's like one real root with a multiplicity of 1 or a multiplicity of 3, but definitely some complex roots in the mix here. Let's go back and see what we can do. So you notice when you look at the polynomial that some of the powers appear to be missing. I'm kind of putting air quotes around that. What that means is that the coefficients of those powers are 0. So for example, you notice there's no x to the 4th term, and likewise there's no x term. And that means that the coefficients are 0, and when you represent this polynomial in a synthetic division array, it's very, very important that all the coefficients are present and accounted for. So in other words, if you write this incorrectly, it's going to be garbage in, garbage out. You have to make sure that everything is there. So if you're doing it right, it's going to look like this. You're going to drop your -2 into the divisor box, and the coefficients are going to be as follows. And just for clarity, I'm going to label them here. So you're going to have a 1 that comes from x to the 5th. You're going to have a 0 that comes from x to the 4th, a 1 from x cubed, an 8 from x squared, a 0 from x to the 1st, and then an 8. And so again, these columns, at least at this stage of the array, represent x to the 5th, x to the 4th, x cubed, x squared, x to the 1st, and x to the 0, right? And so hopefully that root at -2 has a multiplicity of 3. That would be great. It makes it easy for us. Let's see what we end up with here. Bring down the 1. -2 times 1 is -2. 0 and -2 is -2. -2 times -2 is +4. That gives us 5. That's -2 times 5 is -10. So that gives us -2. -2 times -2 is +4. That gives us 4. And then -2 times 4 is -8. And so, as expected, we get a 0 remainder. So since we're checking to see if there's additional multiplicity beyond 1 for this root, it doesn't make sense to report out. We just want to go right back in and try another round of synthetic division to see what we get here. So negative 2 times 1 is negative 2. Negative 2 and negative 2 is negative 4. Negative 2 times negative 4 is positive 8. That's going to give us 13. Negative 2 times 13 is negative 26. That gives us negative 28 right there. And negative 2 times negative 28 is positive 56, so that we end up with a remainder of 60. And so that's kind of tricky, because that means that, well, the multiplicity of that root at negative 2 is only 1. And we're looking for a total of 5 roots. So we probably want to report out to see what we're looking at here. Let's write down what we have. And remember, we're going back to that quotient right there, because this quotient that we got down here at the bottom from dividing by negative 2 once again, that's a useless piece of information. All it really told us is that the multiplicity of negative 2 is 1. So we have found that p of x is equal to, let's see, it's going to be x plus 2. And then the power is going to drop by 1. So as we rebuild that quotient going from right to left, the power on the first term, the coefficient of 1 is going to be x to the 4th. So we're going to have x to the 4th minus 2x cubed plus 5x squared minus 2x plus 4. And that's kind of tough, because I mean, I know right now that if I graph that, I'm happy to show you the graph. I'm not going to get anything from it. It's only going to have complex roots. Check this out. Let's switch back to the calculator and take a quick look at that. So I don't want to erase this one. I'm just going to deselect it so that I can graph something else without having to see, sorry, wrong button there, without having to see the graph of that one. So the one that I want to key in now is what we reported out. So it would be x to the 4th minus 2x cubed and remember, we're telling you in advance that this is basically a waste of time to graph this, because you're not going to get any information from the graph that you don't already know. I just want you to see it with your own eyes. Okay. Let's just standard zoom that. So there it is right there. That is the polynomial that we just reported out. If you go back and look at the iPad, that is the graph of that polynomial right there. And so in this case, the graph doesn't really give us any information. It's a dead end, because we use the graph to see real roots. And we don't have any real roots here. You can see plainly that the graph has no contact whatsoever with the x-axis. And so what that means is that this graph here is going to have complex roots. So we're kind of back to the drawing board here. We have to try something else. And this is a great example, because it shows that, you can't just shut your brain off when you're doing this. You have to kind of keep your background knowledge at your disposal in the form of other tools. So we're not going to be stumped by this, but we are going to have to retrench a little bit. And so something we would like you to notice, basically, let's leave a record here of what we saw. So we graph this. Okay. So one thing that that catches my eye when I'm looking at this is that the polynomial looks like it may be factorable, and it's easy to forget factoring when you're working on complicated polynomials. But factoring is a very important tool, and so let me show you what I mean here. If you were to write this as x to the 5th plus x cubed plus 8x squared plus 8, And you can set it equal to 0 because we are searching for the roots. This looks like it's going to work for factoring by grouping. When you do factoring by grouping, you're grouping the terms 2 by 2, and you're looking for GCFs effectively. So for this particular case, if you look at those first two terms, what's the GCF of x to the 5th and x cubed? It's x cubed. And so if you factor out an x cubed, you're asking yourself, in effect, what am I going to multiply x cubed by in order to make x to the 5th? In order to make x cubed, you're going to have x squared plus 1. And likewise, the last two terms there have a GCF of 8. And so now you realize, oh, I had a GCF of x squared plus 1 that I can extract in this way. And so both of those can be taken by factoring patterns. Let me introduce just a wee bit more space here. So we've seen several examples of x squared plus 1 in action, and we know that that is easily factored. As far as the x cubed plus 8 is concerned, that is a sum of cubes. And that's one of those things that, we hope that you would be able to review, through YouTube or through your text or something like that. If you haven't seen that for a while, the pattern in question is this one. It says, if you have something of the form a cubed plus b cubed, that this is always going to factor as a plus b times a squared minus ab plus b squared. So really all you have to be able to do is to recognize what a and what b is, and then just put that into its location in the formula there. It's like a template, right? So let's color code the factoring to make it clear what's going on here. So as far as the x squared plus 1 is concerned, we know that that's going to factor as x plus I times x minus I, right? And as far as the x cubed plus 8 is concerned, that's going to factor as x plus 2. And then the a squared minus ab plus b squared is going to be x squared minus 2x plus 4. And so we're not quite home yet. We have a quadratic right there, and trust me, it's not going to factor. You're going to have to use quadratic formula. So let's do that right here. If we have x squared minus 2x plus 4 is equal to 0, that would suggest that a would be 1, b would be negative 2, and c would be positive 4. And so if we drop that into the quadratic formula here, we would have x, opposite of b is positive 2, plus or minus b squared. That's going to be 4 minus 4 times 1 times 4. All of that over 2 times 1. So if you simplify, 4 minus 16 is negative 12, and so you're going to have 2 plus or minus negative 12 over 2. The negative 12 can be simplified. The largest perfect square factor is 4. And you're going to extract that 4 and an I squared, and those are going to come out as 2I. So you're going to end up with 2 plus or minus 2I root 3 over 2. And that's going to reduce. You can cancel the common factor of 2 there, and so you're going to end up with 1 plus or minus I root 3. And so at that point, we have our factors, and we can give you our final answer here. We are going to have as follows. So we know that p of x is equal to x plus I times x minus I times x plus 2 times the quantity x minus 1 plus I root 3 and x minus 1 minus I root 3. And when I write complex roots that come from a quadratic formula expression like that, I usually put the I in front of the radical because, my handwriting is kind of iffy sometimes, and it makes it perfectly clear to the reader that the I is in fact outside of the radical and not in. Let's see what we have next here. Let's do one last example just to make sure that you're tracking us here. In fact, if you want, you could pause the video here and you could have at this last example, the 5th degree polynomial you can see in the middle of your screen right there. And by the way, I did decide after the fact to report out from what I obtained in the last example, and so you can see the roots and the multiplicities on display there as well, and that's a good way to answer that type of a question. So here's what's next. Fifth degree polynomial, and let's see how we can do here. I've taken the liberty of keying this into the calculator already. Let's switch over to the calculator. And by the way, one final thing I wanted to mention. You've seen us repeatedly evaluate real roots using the calculator. The calculator can evaluate complex roots, but it requires a change of mode. And so if you're interested in pursuing that, you can search around on YouTube or something, and you can find out how to toggle the mode of the calculator to have it evaluate complex roots without erroring out. If you try in the wrong mode to have it enter or to have it evaluate a complex root, it's going to give you an error message, but it is capable. In my experience, it's usually not wise to shift the mode a lot. It causes a lot of problems for people. Many people are kind of reticent to look up stuff in a manual or whatever, and so it's best just to keep the calculator in the same mode. It makes it smooth, and it means less problems. But you can do what seems good to you. All right, so I have it keyed in, as you can see right there. I'm just going to standard zoom that. See what we get. It looks like we have a root with odd multiplicity at 2. Let's verify that. Indeed we do. So let's switch back to the iPad here. Okay. So we'll do a little bit of synthetic division here, and hopefully we get a multiplicity that's greater than 1, but we'll have to see. So I have coefficients of 1, -2, +2, -4, +1, -2. All the powers are present and accounted for, so we're good to go. Start with that. 2 times 1 is 2. Sorry, that drops out. 2 times 0 is 0. 2 and 0 is 2. 2 times 2 is +4, and that drops out. 2 times 0 is 0. 1 and 0 is 1. 2 times 1 is 2. And so as expected, we get a remainder of 0. Now let's stop and think about what we got from that there. That would be x to the 0. That's x to the first. That's x squared, x cubed, and x to the fourth. Normally I would say don't report out, but I think at this problem here, it's maybe worth to report out. We can try another round if you want. I mean, no harm in seeing, but let's get that stuff out of the way first here. I don't think we're going to get a multiplicity of 3, but I could be wrong. Let's try that. So another run with 2. And the reason I say that, by the way, is because you notice how all the coefficients are in the quotient there that we're going to be redividing. They're all positive. And so unless you have a mix of signs like you have in the original dividend, you're going to end up with a buildup of value. You're not going to get anything dropping out like we would get in the first iteration of our division there. So I think that this is going to not go in evenly, but let's see. 2 times 1 is 2. 0 and 2 is 2. 2 times 2 is 4. 2 and 4 is 6. 2 times 6 is 12. You see what I mean? 0 and 12 is 12. 2 times 12 is 24. 1 and 24 is 25. So it's plain to see that that is not even division. And that means that we basically have a multiplicity of 1 on that root. So since this is a 5th degree polynomial and we know we're hunting for 5 roots, having a multiplicity of 1 on that means that there's got to be complex roots. And there's either 2 or 4, we have to figure out what the multiplicity is going to be and what the roots are. So here's what we have right now. We have p of x. And we found that x minus 2 goes in. And when it does, you're left with x to the fourth plus 2x squared plus 1. And so it might seem like we're kind of back to the situation where we had a prior example that kind of turned out to be difficult, and there was the appearance of a dead end, but we were able to, navigate out of that. This one is kind of similar. What you have to notice here is that this polynomial is quadratic in form, meaning it's quadratic, especially if you do a change of variables, you can see it. But if you have good factoring, you can factor it without doing a change of variables. Here's what's going to happen. You're going to have p of x, and it's x minus 2. And then it turns out that that's going to factor as x squared plus 1 quantity squared. So if you want to be more explicit about what that means, it means, because we know how x squared plus 1 factors, yeah? It's x plus I times x minus I. So we're going to have x minus 2, and then we're going to have x plus I and x minus I quantity squared. Now, I don't think your learning management system is going to be wild about that particular expression, so I'm assuming you're going to have to put it in as follows. It's going to be x minus 2, x plus I quantity squared, and then x minus I quantity squared. And so if you're listing the roots and the multiplicities, you'll be middle-aged too, and you'll have a hard time spelling when you're middle-aged. You have a root at 2 with a multiplicity of 1. And then you have a root at plus or minus I, and it's 2 each. Because the power, of course, on the factor there was 2, right? So a very nice little problem. And if you did not have your factoring skills up to speed where you would notice, that x squared plus 1 squared is x to the fourth plus 2x squared plus 1, you could have used quadratic formula at that stage right there with a change of variables, or with some good skills. You don't necessarily have to do the change of variables, but it probably helps to illuminate the structure. So I'm not going to show that. I think this video is probably getting long enough as it is. One other thing, if you want to try, let's go back to the slides here real briefly. If you want to test your abilities, you could try to get the complete factorization for those 3 polynomials that you see right there on the screen, f of x, g of x, and h of x. And you could pause the video right now and work those out. I'll show you the answers in just a second here. So it can be shown, I'm not going to show it, but it can be shown that the factorizations of those 3 polynomials are as follows, right there. So hopefully this has been helpful. Stay tuned. We have some additional videos that cover this chapter regarding rational functions.